projectile motion problems are similar to free fall, but instead of just falling up or down, you're also going to be moving horizontally. So you're moving in 2 dimensions. You solve these the same way you did free fall, but you're going to add in the constant motion that we did from the first chapter. So it's going to look like this. In this situation, you run off an 8-meter high platform. So to draw this out, you got this platform that's 8 meters up in the air. That's an 8. So you're going to run off this platform and ultimately fall 8 meters into the water below. Now you ran off horizontally. This is where the problem becomes important. You have to read for direction. Horizontal velocity. So we would call that's 5 meters per second horizontally. So we didn't jump up, we didn't jump down, we just ran straight off this thing at 5 meters per second, fell 8 meters, and then it wants to know, well, how far should you place a cup of water to get caught? So to set this up, because we're moving forward and down at the same time, we need to separate our variables, horizontal variables, from vertical variables. We're basically doing 2 problems, one for the horizontal, one for the vertical. So for these, we're going to have two sets of variables. We're going to have horizontal, so I'm just going to make an X column and a Y column. I'm going to move this up. So horizontally, all they said was that you ran off this platform at 5 meters per second. So that's a speed or velocity. So that's v. It was horizontal, so we put an x, and then it was at the beginning. It was our initial speed. So we're just going to put a subscript 0. So it's vx naught is 5 meters per second. They asked for dx. How far horizontally should this thing be placed away? So those are all our horizontal variables they gave us. Now they also gave us a vertical reference of that you fell 8 meters. So that's a distance, so displacement, that's a d, and then we're going to put the subscript y to reference the up and down. Over here we did the subscript x to reference left and right, or horizontal. So here for the vertical, we fell 8 meters, so it's a negative 8 meters, just like we did with free fall. So there's our set of variables. Where do we start? I always find it easier start with the question. Some of you are going to memorize these and know that you need you're missing something right now. But how do I know I'm missing something? Start with the question. The question's going to tell us what we're missing. So we're looking for dx. The only horizontal equation in the horizontal direction for projectile motion, to remind you, you don't speed up or slow down. If someone tosses you a ball, so if I'm here playing catch and I throw a ball to you, you catch it here, I threw it here, horizontally, it moves across the field at the same speed. This is always the same v. You don't see someone doesn't throw you a ball and last minute it speeds up all of a sudden. It travels across that field at a steady speed. Now up and down it does change because of gravity. Gravity is going to slow it down to the peak and then speed it back up to you. So vertically it does change, but horizontally it maintains that same forward speed. So whenever we're doing horizontal problems, our equation is going to be that constant motion equation that we did the very first chapter. So we're going to start there. We're going to do Vx equals dx over t. Plug in what you know. Well, all we know is Vx, and that's Vx naught. I don't always write the naught because remember, it doesn't change. So whatever it was at the beginning, it's that speed all the way through. So Vx is Vx naught. You don't have to make a distinction there. So we get 5 equals dx over t. Now what this tells me is, for me to find dx, I need time. Now again, you can memorize that, and maybe you got that from reading the problem. You realized, hey, I'm missing time, but let the problem do it. I didn't have to think ahead. I started where it wanted me to start, with dx. So now where do I go from there? Well, I got to find t. Well, I can't find it. I can't find that t from this equation. So I need to come over to my verticals. I need more information. Well, vertically, I know the acceleration was due to gravity, which is a negative 9.8 meters per second squared. There's a square there. I just can't add it. So with the vertical, we got dy is a negative 8 meters. We're looking for time, and we have the acceleration is free fall because it's falling. So again, back to free fall. The only equation that had dy, t, and g, there is only one. The other option is we don't know how fast. We don't know the final velocity when it hits the ground. That's the other hint of what equation we should use. So the only equation that didn't have final velocity in it was this dy equals Vy naught t plus 1/2 gt squared. So dy was a negative 8 meters. You fell 8 meters. The Vy naught, V is how fast, Y is vertical, up and down, and then that 0, it means at time 0. So Vy naught is how fast you were going vertically at the very beginning. You weren't. You didn't jump up or down. So that's 0, and then 0 times anything is 0. So then we got plus 1/2 negative 9.8 t squared, and we can solve this for t. We divide both sides. Half of 9.8 is 4.9, so you take 8 divided by 4.9 and square root it. You get a time of 1.27 seconds. We can take this time, plug it back into this equation to get our final answer, our distance. So I'd come back up here and say 5 equals dx over 1.27, and dx is going to equal 6 meters, roughly.